Welcome everybody once again. So we are in our fourth module, that is Kani'S method. We are studying how to analyze indeterminate structures using Kani'S method. So in the last class we saw what is Kani'S method and about the procedure, how to analyze a continuous beam using Kani'S method. Today we will solve a problem. So this is our first problem. So today we are going to analyze a 3-span continuous beam with fixed end supports. We will move on to the problem. Our problem is a continuous beam ABCD consists of 3 spans and is loaded as shown in the figure. Ends A and D are fixed. So end supports are fixed. Determine the bending moments at the supports using Kani'S method. Also plot the bending moment diagram and the deflected shape of the beam. So last class we saw the procedure, we saw the step-by-step procedure how to analyze an indeterminate structure using Kani'S method. So our given problem is, it is a 3-span continuous beam ABCD. So AB is one span, BC is another span and CD is the third span. The span lengths are the span AB. The AB is of span 6 meter, BC is of span 5 meter, CD is of span length 5 meter. In this span AB we have a UDL of 2 kilonewton per meter. In the span BC we have a concentrated load of 5 kilonewton acting at a distance of 3 meter from B. In the span CD, we have a concentrated load of 8 kilonewton acting at a distance of 2.5 meter from C. That is acting at a center of the span CD. The moment of inertia R for the span AB, moment of inertia is I. For the span BC, moment of inertia is 2I. And for the span CD, the moment of inertia is I. This is our given problem. So solution, as usual, the first step is to find the fixed end moments. We have to determine the fixed end moments. So we know for finding the fixed end moments, we will be assuming all the supports as fixed. So when we consider all the support as fixed, when you consider the span AB, A is fixed support and B is fixed support. That means at the fixed support, we will have hogging moments or negative moments. So when you take a section in the span AB, the left anti-clockwise becomes negative and the right clockwise becomes positive. That is why when the fixed moment at A, when the far end is B, is minus, it is negative anti-clockwise, minus WL square by 8. And for M of BA, that is fixed end moment at B, when the far end is A, at B it is clockwise, so positive plus WL square by 8. This is for UDL. When it is UDL, it is WL square by 8. So what we get is minus WL square by 8. So here in the span AB, the UDL is 2 kilonewton per meter. So minus 2 into the span length is 6 square divided by 8. Sorry, it is not 8, it is minus WL square by 12. Fixed end moment is minus WL square by 12 and plus WL square by 12. So minus 2 into 6 square divided by 12, we get it as minus 6 kilonewton meter. Similarly, the fixed end moment M of B is equal to plus WL square by 12. So plus 2 into 6 square divided by 12, we get 6 kilonewton meter. Now we will move on to the span BC. See, when we are considering the span BC, again BC, so we will consider the span BC. For finding the fixed end moments, we will assume the supports are fixed. If the supports are fixed, our moments at the fixed ends are hogging. That means negative. You take the section. So left will be anti-clockwise and right will be clockwise. That is why M of BC, fixed moment at B when the far end is C, is negative, and fixed moment at C when the far end is B is positive. The formula is, since it is concentrated load, there is a concentrated load acting at a distance of 3 meter. We will consider this as A. So our formula is W A square B by L square for at B, and at C the fixed end moment is plus W A B square by L square. So by substituting the values we get minus W is given here as 5. So 5 into A is 3 meter, B is 2 meter. So totally 5 meter for the span BC. So 3 square multiplied by 2 divided by length is 5, 5 square. We get M of BC as minus 2.4, minus 2.4 kilonewton meter. Similarly, M of CB is plus 5 into A square. A square is, sorry, A is 3, B square is 2. 2 square divided by L is 5. 5 square. We get it as plus 3.6 kilonewton meter. Now we will consider the span CD. So while we are considering the span CD, so we will assume C as fixed and D as fixed. We have a concentrated load of 8 kilonewton. So here this is acting at a distance of 2.5 meter. Total length of the span is 5 meter. That means it is acting at the mid span. So we know the formula is the left will be anti-clockwise and the right moment will be clockwise. Okay, because negative. When you are taking the section, the left anti-clockwise is negative and the right clockwise will be negative. Then only you will get hogging moment. So, our formula is W A square B by L square. You substitute A equal to L by 2. So, L square by 4. B is L by 2 into L square. You get W L by 8. Okay, that is why it is minus W L by 8. Similarly, M of DC also, you substitute A equal to L by 2, B equal to L by 2, you will get plus W L by 8. So, we will substitute the values. We get minus, so W is 8 kilonewton, 8 into L is 5 meter, so 5 divided by 8, we get minus 5 kilonewton meter. Similarly, M of DC is equal to plus W is 8, L is 5 divided by 8, we get plus 5 kilonewton meter. So we have found the fixed end moments. Now, step 2, we will find the rotation factor. In the moment distribution method, step 2, we found the distribution factors. In Kani'S method, we have to find the rotation factors. As we have studied in our last class, rotation factor is nothing but minus 0.5 times of the distribution factor. That is minus half of the distribution factor is rotation factor. Right? Minus half of the distribution factor will give you the rotation factor. So now, first of all we will find the distribution factor, then we will multiply it by minus half, that is minus 0.5, we will get the distribution factor. So for finding the distribution factors, first of all we will consider the joints. So the joints where more than one member acts, where more than one member meets. Here we have two joints where more than one member meets. That is joint B and joint C. At joint B, we have the members BA and BC. At C, we have the members CB and CD. Now, we know the relative stiffnesses. If the far end is fixed, the relative stiffness is I by L. And if the far end is hinged, the relative stiffness is equal to 3 by 4 of I by L. So here everywhere the far end is fixed. The intermediate supports also should be considered as fixed supports. So everywhere the relative stiffness is I by L. Okay. Now, so we will consider the joint first. So we have two joints, joint B and joint C. At joint B we have members BA and BC. At joint C we have members CB and CD. Now we will find the relative stiffness. Everywhere it is I by L. So for the span BA, I is given as 2I. You can check it in the diagram. For the span for the span BA, I is I. For the span BC, our I is 2I. So for the span BA, it is I divided by the length of the span is 6 meters. So it is I by 6. For span BC also it is I by L because the far end is fixed. But I is equal to 2I here. So 2I divided by 5. Now we will consider the span CB. So for CB, the far end B is intermediate support. So we will consider it as fixed support. So our relative stiffness is I by L. So for the span CB, I is given as 2I. So 2I divided by 5. And for the span CD, D is fixed support. So I by L. Here I is given as I. I divided by L is 5. Now we will consider the sum. We will take the sum, that is I by 6 plus 2I by 5. We get 17I by 30. Similarly, 2I by 5 plus I by 5, we get 3I by 5. Now we will find the distribution factor. So we know distribution factor is equal to the sum as sigma k. It is k by sigma k. Distribution factor is k by sigma k. So I by 6 divided by 17 I by 30, we get 5 by 17. Similarly, 2I by 5 divided by 17 I by 30, we get it as 12 by 17. You add these both, we will get 1. 5 by 17 plus 12 by 17, we will get 1. Similarly, for the joint C, 2I by 5 divided by 3I by 5, we get 2 by 3. I by 5 divided by 3I by 5, we get 1 by 3. So add 2 by 3 plus 1 by 3, we will get 1. So summation of distribution factor at the joint will be equal to 1. Now we will find the rotation factor. So we know the rotation factor is equal to minus 0.5 times the distribution factor. So our rotation factor is 5 by 17 multiplied by minus 0.5, we get minus 0.147. Similarly, 12 by 17 multiplied by minus 0.5, we get minus 0.353. Again, 2 by 3 multiplied by minus 0.5, we get minus 0.333. And 1 by 3 multiplied by minus 5, minus 0.5, we get minus 0.167. So second step is over, that is we have found the distribution factors. Now the third step, we have to find the resultant restraint moment. So resultant restraint moments we will find with respect to the joints. That is, see, we have two intermediate joints B and C. So this resultant restraint moments should be determined at joint B and joint C, and it is represented by the symbol MFI. So here I is B and C. We have two intermediate joints B and C. So I is B and C. So MFI, F represents the restrained moment here. So MFI means restrained moment at I. So MFB means resultant restrained moment at B, and MFC means resultant restrained moment at C. So it is the summation of all the members meeting at the joint. Summation of all the fixed end moments meeting at the joints. So at B we have the members BA and BC. So MFB will be equal to MFBA plus MFBC. Okay. So that is the meaning of this. So summation of all the fixed end moments meeting at that joint. So that is equal to MFBA we have found as in our first step. In our first step fixed end moments we have calculated it as plus 6. And MFBC is calculated as minus 2.4. So we get plus 3.6 kilonewton meter. And MFC at C we have two members joining at C, MFCB and CD, right? CB and CD. So fixed end moments at C, summation of all the fixed end moments at C. That is MFCB plus MFCD, that is equal to MFCB is plus 3.6 minus 5, which we have determined in our first step, that is equal to minus 1.4 kilonewton meter. Okay, now see, remember this 3.6 and minus 1.4. Now our step 4, we will draw our Kani'S figure, Kani'S diagram. Step 4 is the Kani'S iteration process. So how will we undergo this Kani'S iteration process? We have studied in our procedure in the last class in detail, the theory part. So now, for every Kani'S iteration process, we will have, for every intermediate joints, we will have a small box and a bigger box, or small circle or a greater circle. So here we will draw a small box and a bigger box. Okay, so first of all we will draw a small box for joint B and another bigger box. Okay, this is for joint B, and this has to be drawn only for intermediate supports. So this is joint B, and for joint C we will draw another small box and another bigger box. So this is for joint C. Now see, we have found our restrained moments at B and C, right, in the last step. That is, we have found the resultant restrained moments at joint B and at joint C. So these moments, that is plus 3.6 and minus 1.4, should be written inside the smaller box. So at B we have the resultant restrained moments are plus 3.6 kilonewton meter and minus 1.4 kilonewton meter. Restrained moments at B and restrained moment at C. So actually when this is B and C, right? So now we will write the fixed end moments. So what is our fixed end moments? We have what we have determined in our first step. So for writing the fixed end moments, see, this is B and C. Now we have two more joints, A and D. So we will write this as our joint A. Joint A, we don't have more than one member, only one member at the joint A. So we will take this as joint A, this as joint D, and this is the beam joining B and C. So in our first step, we have determined our fixed end moments, right? Fixed end moments. So M of AB, M of BA. For the span AB, fixed end moments are minus 6 and 6. Minus 6 and 6 kilonewton meter. So it is minus 6 and plus 6. Minus 6 kilonewton meter and plus 6 kilonewton meter. So these are the fixed end moments. Again, for the span BC, the fixed end moments are minus 2.4 kilonewton meter and 3.6 kilonewton meter. Now for the span CD, the fixed end moments are minus 5 kilonewton meter and plus 5 kilonewton meter. Okay. Now we have to write the rotation factor. See, whatever we have found in the first 3 steps, you have to write it inside the Kani'S iteration process. So here we are writing the restrained moments. First of all, you write the restrained moments inside the smaller box. Then write the fixed end moments. After this, we are going to write the rotation factor. So the rotation factors, we know, we have already found rotation factor will be for intermediate joints. So for B, we have found the rotation factor as, for BA and BC, it is minus 0.147 and minus 0.353. So for BA, it is minus 0.147 and for BC, it is minus 0.353. So that we have to write here. See, for BA, it is minus 0.147. For BC, it is minus 0.353. Write vertically, okay? Again, at joint C, for CB, the rotation factor is minus 0.333 and for CD, the rotation factor is minus 0.167. Now we will go for the iterations. See, as I have told you earlier, Kani'S method is an iteration process. So now it is time for our iteration. So how will we do the iteration? So for that, we will draw the lines first. So it is A. We will close it, right? So A and D. Draw a line at B and at C. That means AB, BC and CD. So in the iteration, we have to find the small MAB. What is small MAB? That is the rotational contributions. So we will write, see, this is our M of AB, right? These are M of AB, fixed end moments. See, these are our fixed end moments. Now we will find MAB, that is rotational contribution of AB. That is rotational contribution of end A to MAB. That is the meaning of that. Rotational contribution of end A to MAB. That is moment at A when the far end is B. Rotational contribution. MAB means rotational contribution of end A to MAB. That will be our final moments. MAB is our final moments. That is MAB. Similarly, here we will be finding MBA That is rotational contribution of end B to MBA. Okay, to capital MBA. That is the meaning of that. So small MBA. Here we will be writing small MBC, MCB, MCD and MDC. So our aim is to find the rotational contributions. So for this we will go for iterations. So iteration 1, iteration 2, iteration 3, etc. Okay. So our iterations. So we will go for 5 iterations. See, as your iteration goes on, you will get more accurate results. We will go for 5 iterations. So I will write here as iteration 1, iteration 2, iteration 3, iteration 4 and iteration 5. We will stop with iteration 5. Now, how will we find this MAB, MBA, small MBC, this rotational contributions? How will we determine these rotational contributions? So first of all, for the first iteration, that is cycle 1, okay, iteration 1. So that we will find here, that is step 5 Kani'S iteration cycles. So iteration 1 or cycle 1. So iteration number 1. So first we are going to find MCB. We'll start from here. Okay. So initially, see, these both are contributing. These both, that is MBC and MCB, will be contributing to each other. Initially, we will assume MBC is equal to 0. That means initially we will assume the first rotational contribution will be equal to 0. That means we will start with this MCB. So MCB is equal to, we know our MFC, that is, this is our restrained moments, right? This restrained moment into the rotational factor will give you MCB. So MCB is equal to that is the restrained moment at C, restrained moments at C. MFC, what we have found it in our third step, MFC, that is the restrained moments, resultant restrained moments multiplied by the rotational factor RCB. So we know MFC, the restrained moment is minus 1.4. So it is minus 1.4 multiplied by rotational factor RCB is minus 0.0333. So minus 0.333, we get plus 0.466. So M of CB is equal to, for the first iteration, M of CB is equal to plus 0.466. So plus 0.466. Now we will find MCD. So MCD is also equal to MFC multiplied by RCD. So that is minus 1.4 multiplied by minus 0.167. Minus 0.167, it is plus 0.234. So it is plus 0.234. Now we will determine MBC. So now MBC will be equal to this rotational factor, that is RBC multiplied by MFB, restrained moment at B, plus MCB. See, that is, initially we have assumed this as a 0. See, actually this is nothing but RCB into MFC plus MCB. Initially we assumed this MCB is equal to 0. That is why first it is only MFC. Now we have determined this rotational contribution at a joint C. This is the rotational contribution at a joint C. So since we have determined the rotational contribution at a joint C, now we have to consider this MCB also. Okay. So that will be equal to RBC is minus 0.353. So minus 0.353 multiplied by MFB is plus 3.6 plus MCB, we have found it as 0.466. Okay, this. See, only this will contribute to this joint. Similarly, only BC will be contributing to this joint. Okay, only this rotational contribution will contribute to this joint, and only this factor will contribute to this joint. So this we will not consider. This will not be considered. This will not be considered while calculating MCB or MCD or etc. So MBC will be equal to minus 1.435. So it is minus 1.435. Now we will find what is MBA. So MBA will be equal to RBA multiplied by MFB plus MCB. So that is why I told, see, only this will be contributing to this joint and only this will be contributing to this joint. Okay. That is why both it is MCB. Only MCB will be contributing to the joint B. So we get RBA will be equal to, RBA is minus 0.147. Minus 0.147 multiplied by plus 3.6 plus 0.466, we get minus 0.598. So first cycle is over, minus 0.598, minus 0.598. Here in the fixed supports, no, you will not have any rotational distributions. Okay, because there is no distribution from fixed support to the intermediate support. Okay, there is no rotational distributions from fixed support to the intermediate support. If the far end is fixed, if the extreme supports are fixed, the rotational contributions to the neighboring support will be equal to 0. Okay, see, if the far end is fixed, it will carry all the moments. There is no rotational contribution from fixed support to intermediate support. Only the contribution is from intermediate support to the fixed supports. So first iteration is over. Now we will move on to second iteration. Okay, we will move on to second iteration. So we will take it as iteration 2. So second is iteration 2. So iteration 2 also we will start as we did in the first step. MCB. So MCB will be equal to RCB multiplied by MFC plus. So now which will contribute? This MBC will contribute. So MBC. MBC. So that will be equal to minus 0.333 multiplied by M of C is minus 1.4. M of BC, we have determined it as minus 1.435. So minus 1.435, we get plus 0.944. So MCB is plus 0.944 plus 0.944. Similarly, MCD. Okay, now we will find what is MCD. So MCD will be equal to RCD into M of C plus MBC. So that is minus RCD is minus 0.167 multiplied by minus 1.4 minus 1.435. We will get the rotational contribution as plus 0.473. So it is plus 0.473. Now we will find MBC and MBA. So MBC will be equal to RBC, same thing, RBC multiplied by MFB plus MCB. So that is minus 0.353 multiplied by plus 3.6. Now what is MCB? See, it has changed in the second iteration. MCB is plus 0.944. We get minus 1.604. So it is minus 1.604. Similarly, MBA will be equal to RBA multiplied by MFB plus MCB. So it is minus 0.147 multiplied by plus 3.6 plus 0.944. We get minus 0.668. So it is minus 0.668. So here we don't have any values, right? So extreme supports are fixed supports, so we don't have any rotational contributions. Now we will move on to our third iteration. So third iteration 3. So iteration 3, the same procedure, the formula is the same, but only thing where, see, RCB is not going to change. These things do not change, right? Fixed. This is also fixed. Now MBC changes. Instead of MBC, so for here it is minus 1.435. For the third iteration for MBC, you have to use this value, that is minus 1.604. Similarly, in these two cases, see, these things do not change. For MCB, you have to use what you will get in the third iteration. Third iteration, you will get one value for MCB. You have to use that value. Okay. So MCB, you will be getting a value. So that value you have to use here for MCB. So third iteration. Anyway, first problem we will do it in detail. Okay. So cycle 3, MCB is equal to RCB, MFC plus MBC. So we get minus 0.333 multiplied by minus 1.4. MBC is this value, minus 1.604. Minus 1.604. We get plus 1.0. So MCB is plus 1. Now MCD will be equal to RCD into MFC plus BC, that is equal to minus 0.167 multiplied by minus 1.4 minus 1.604, we get plus 0.502 plus 0.502. Similarly, MBC is equal to RBC into MFB plus MCB. So we get minus 0.353 multiplied by plus 3.6. Now for MCB, you have to use this value plus 1. So it is minus 1.624. So minus 1.624. And MBA will be equal to RBA MFB plus MCB. That is minus 0.147 multiplied by 3.6 plus 1. We get minus 0.676. So minus 0.676. Similarly, we will do iteration 4 and iteration 5. So you can solve it similarly. Okay, continue, proceed with the same procedure. So the values are, I will write the values directly here. So the fourth iteration, we will get the value as plus 1.007 plus 0.505 minus 1.626 and minus 0.677. And we will get the fifth iteration as plus 1.008 plus 0.505 minus 1.627 minus 0.677. So here we will terminate our iteration because there is no change in the values of Mij as compared to the corresponding values in the fourth cycle. See, almost similar values you have obtained, almost similar. Closer values you have obtained. So we will stop with this. That's why I told you, as you go on for large number of iterations, you will get more accurate results. So these are our final values of contribution. See, final values, that is MBA is equal to minus 0.677. MBC will be equal to minus 1.627. MCB is plus 1.008 and MCD is plus 0.505. Okay, so these are our final contribution of rotational components. Okay, so we will write final contribution of rotational components. So that will be our step 6. So step 6, our rotational components, rotational contributions. Okay, so our rotational contributions are MBA, MBC, MCB and MCD. So MBA is minus 0.677, MBC is minus 1.627, MCB is plus 1.008 and MCD is plus 0.505. Now we will determine our last step, that is computation of final moments at the joints. That is our step 7. Step 7 is computation of final moments. So how will we find our final moments? See, I have told you in detail in the last class, in the theory part. The Kani'S method and moment distribution methods are the extensions of slope deflection equations. So Kani'S method is also an extension of slope deflection equation. We know the slope deflection equation MAB is equal to M of AB, that is fixed end moment at A when the far end is B, plus 2EI by L into 2 theta A plus theta B. Right? So this is our slope deflection equation. So this equation we have rewritten as M of AB plus 2 times. So 2 EI theta A by L is M AB plus 2 EI theta B by L is M B A. So our final moment is MAB is equal to fixed end moment plus 2 times the rotational contribution of A to the moment MAB plus 1 time the rotational contribution of joint B to the moment MAB. Okay, that is the meaning of that. So now we have obtained this fixed end moment in our first step. Using the Kani'S cycle, Kani'S iterations, we have determined the rotational contributions MAB, small MAB and small MBA. Right? So now we will open a tabular column to find our final moments. So we know our final moments. Final moments are MAB. It will be written in terms of MAB, MBA, etc. Right? So we will write it as MIJ. So MIJ means that is nothing but MAB, MBA, MBC, MCB, MCD and MDC. Because we have 3 spans, right? Now, so this is our final moments. Okay, MIJ. So that is equal to the fixed end moments MFAB. So that we will write here. The second column we will write MFIJ. That is the fixed end moments. So fixed end moments are nothing but MFAB, right? So MFAB we have calculated in our first step as minus 6 kilonewton meter. MFBA is plus 6 kilonewton meter. MFBC is minus 2.4 kilonewton meter. MFCB is plus 3.6 kilonewton meter. MCD is minus 5 kilonewton meter. And MDC is plus 5 kilonewton meter. So this is over. Now M2MIJ, right? 2MIJ. So that is 2 times MIJ. So 2 times MAB. So we don't have MAB. So that is equal to 0. 2 times MBA. So MBA is minus 0.677. So 2 into minus 0.677 we get minus 1.354. So it is minus 1.354. Now 2 times, see IJ means BC, right? 2 times MBC. MBC is minus 1.627. So 2 into minus 1.627 we get minus 3.254. Minus 3.254. Now 2 times IJ is CB. So 2MCB. 2 MCB, that is 2 into 1.008, we get 2.016. So plus 2.016. Next, it is CD. IJ is CD, right? So 2 MCD. 2 into MCD, that is 2 into plus 0.505. We get plus 1.010. Again, we don't have MDC, so that is 0. So this part is over. Next it is MBA. That means M. So this is MIJ. This is MJI. Okay. So it is MJI. So next we will write MJI. JI means MBA. MBA should be written here. J is B, I is A. So what is MJI? That is MBA. MBA is minus 0.677. Minus 0.677. Now MAB. MAB we don't have, that is equal to 0. Next MCB. MCB is plus 1.008. Next is MBC. Right? MBC is minus 1.627. Next MDC we don't have, 0. MCD plus 0.505 plus 0.505. Now we will find what is MIJ. So our final step, MIJ will be equal to M of Ij plus 2MIJ plus MJI. That is the summation of all these things. Summation of all this together will give you the final moments, final end moments. So our final end moments are, add these both, minus 6 plus 0 minus 0.677, we get minus 0.677 kilonewton meter, plus 6 minus 1.354 plus 0, we get plus 4.646 kilonewton meter, minus 2.4 minus 3.254 plus 1.008, we get minus 4.646 kilonewton meter, plus 3.6 plus 2.016 minus 1.627, we get plus 3.989 kilonewton meter, minus 5 plus 1.010, we get minus 3.989 kilonewton meter, and plus 5.00 plus 0.505, we get plus 5.505 kilonewton meter. Now these are our final end moments. We can draw the bending moment diagram after finding the simple beam moments also, right? Okay, so step 8 we will find the simple beam moments. So simple beam moments for the span AB, we have an UDL of 2 kilonewton meter. So it will be a parabola. The formula is, it will be a parabola. The formula is WL square by 8. So we get 2 into L is 6. So 6 square divided by 8. We get 9 kilonewton meter. Similarly for the span BC. For the span BC, we have a 5 kilonewton load at a distance of 3 meter from B. So totally 5 meter. So the maximum moment will act at the point where the concentrated load acts, and the value will be equal to WAB by L. So 5 into 3 into 2 divided by 5, we get 6 kilonewton meter. And for the span CD, again it is 5 meter. A concentrated load of 8 kilonewton is acting at the center. So the maximum value will be at the mid span, and it is WL by 4. So 8 into 5 by 4. You can substitute A equal to L by 2, B equal to L by 2. We get WL by 4. So 8 into 5 by 4. So we get 10 kilonewton meter. So for drawing the final bending moment diagram, first of all we will draw the simple beam moments. Then we will draw the final moments. Okay. Okay. We will draw the bending moment diagram first. So for drawing the bending moment diagram, first of all we will draw the simple beam moments. So simple beam moments for AB, it is a parabola because it is UDL. It is 9 kilonewton meter. For BC, the maximum value will be at the point where the concentrated load acts. So the value is 6 kilonewton meter, and for CD it will be at the center of the span, and that is where the concentrated load acts, and the value is 10 kilonewton meter. Now we will mark the end moments, right? That is, we have obtained here in our step 7 computation of final moments, right? So MAB is minus 0.677, MBA is plus 4.646, minus 4.646. Okay, see, that means for AB, when you are considering AB, it is minus anti-clockwise, and then it is BA is clockwise. So your end moments will be like this. It is pointing towards the up, right? So you can write minus 0.677, and it is 4.646. Okay, we will mark this first. So here the values are, sorry, it is not 0 point, it is a 6 point. It is 6 point. So our bending moment this is 6.677 and this is 4.646. Okay, we get 6.677, 4.646. Now we will consider the span BC. See, for the span BC, at B, for BC, it is minus 4.646 anti-clockwise, pointing upwards. CB plus 3.989 clockwise, pointing upwards. So our bending moment diagram will be 4.646 and 3.989. Okay. See, in other words, this is left. If you are bending moment, this is nothing but at the supports you have hogging moments. So it is 4.646 and 3.989. Now we will consider the span CD. So when you are considering the span CD, for CD it is minus 3.989 anti-clockwise pointing upwards, and for DC it is plus 5.0505 pointing upwards. So it will be like this. Okay. So minus 3.989 and here it is 5.505. So your net bending moment diagram will be like this. Negative. This is your net bending moment diagram. See, this means here you have negative moments, positive moment, negative moment, positive moment, negative, positive and negative. That will give you the sagging and hogging details. So this is our bending moment diagram. Now we will draw the deflection diagram. So deflection diagram, this is A, D, B and C. So we have point of contrafluxures at this point, here, here, here and at this point we have point of contrafluxures. So our deflection will be okay, this is our deflection diagram. These are the points of contrafluxure where the bending moment changes its sign, that is from sagging to hogging and from hogging to sagging. So that's all. And if you need to find the shear forces or shear force diagram, you can use the static equilibrium equations and you can determine your shear forces and the reactions at A, B, C, D, etc. You have studied it in detail in your first module. Okay, you can use that concept. So thank you. We will see more problems in the next class.